Grade 11s, we're looking at sinusoidal functions. Day 7, we're investigating models. So this is where the real life comes in. So we're going to do just a couple problems tonight. This one is about harbor depth. So the water depth in a harbor is 21 meters at high tide and 11 meters at low tide. One cycle is completed every 12 hours. Find a function for the water depth as a function of time, t in hours, after low tide, and draw a graph of the function for 48 hours after low tide. I would look at my word problem for a moment and glean the information and just kind of make a list of the things that I know. So I know that I have a maximum depth of 21 meters and I have a minimum depth of 11 meters. You could talk about a peak and a trough, maximum, minimum, doesn't matter, but you've got those two highs and lows. So you know that in between those two, the axis of rest is in between. So if you can eyeball it, great. Otherwise, we would average the peak and the trough, and we're going to get that axis of rest. So 11 and 21, averaging them, we will get 16. It's 32 over 2, which is 16. So we've got the axis of rest, the highest and the lowest. So since our axis of rest is at 16, and the 21 would be 5 above it, and the 11 would be 5 below it, then our amplitude is 5. If you're not quite sure, you would find the difference from the highest to the lowest. So that's the total distance between the two, and divide by 2. And that will give you 5. What else do we know? We know the period is 12. It completes a cycle every 12 hours. So that is something else I know for my graph. It might be a little trickier to come up with the equation, but let's start with the graph. Even though they listed in the other order, I would find it easier to draw the graph first. So I'm not going to do a graph with a wonderful scale. We're just going to get ourselves into the mode here. So I know that I have my lowest is at 11 and my highest is at 21. And the axis of rest is right in between them at 16. So just to get a sense of what this looks like, my graph is going to oscillate about that axis of rest. It starts, we wanted our graph to start at low tide. So draw a graph of the function for 48 hours after low tide. So I know my graph is going to start at the 11. I want to have a cycle every 12 and I want to show it for 48. So I definitely want the numbers 12, 24, 36, and 48. And I should label my axes. So I've got my time in hours and I have depth. I believe in meters. Yep. So I've got my graph sort of started and I know one cycle every 12 hours. So it starts on the low tide, goes to high tide, back to low tide in 12 hours. So I get my beginning point and my ending point, and then I think for a second that the middle is going to be at the high, and I would draw my curve to match that data. There, we have one cycle. Each cycle is 12 hours, so I'll do another one because we want to do it for 48 hours. Okay, that one wasn't as pretty. 2, 3, and 4. Okay, seems to be growing, getting deeper. All right, here's our graph relatively. I find it easier to list my key features and then graph it and then come up with the equation. So our equation will follow the form depth in terms of time. I know my amplitude is 5. I'm going to leave a little space in case I want a negative sign. And I have to decide whether I want to use a sine function or a cos function. A cos function starts at a high, maximum value, and does its cycle through low back to high again. A sine function starts sort of in the middle as you're headed on the upward. This one most closely looks like a cos function, most like a cos function upside down. Just remember our parent function for cos is high, low, and so on. This one is the exact opposite. So I think the easiest way to do this is an upside down cos function. There. Then I need to decide whether I have any horizontal changes. So that would be what goes in the brackets. My period is not 360. So I need to adjust the period so that the cycle is in 12 hours and not 360 hours. So whatever number I put here in front of the t will allow me to have a period of 12. So 360 divided by whatever that number is should give me 12. 30 is the number that I want there. 360 divided by 30 is 12. I have not moved this function to the right, or to the left. It is exactly upside down of a parent cos function, so I don't need anything else in the brackets. And then I need to decide if I've moved my function up or down from a normal parent function centered around the x-axis, and I have. I've moved it up 16. So I've used all my key features to come up with an equation. There are lots of other possibilities if you saw it differently than I did. For instance, if you thought it was a cos function, or here's another possibility. You liked using cos, but you didn't think of it as cos upside down. So you saw a cos function that starts here from a high back up to a high again, which is a cos function that's been moved over. It's been moved over 6. So you can write it as 5 cos 30 t to the right 6 plus 16. Either one of those functions is correct. Some students would rather use sine. Here's a third possibility for the same function. So if you used a sine function starts in the middle as you're headed upwards. So our parent function for sine looks like that, which would start where I have the red dot on our graph. This could be a sine function that's been moved over 3, 1/4 of the distance to 12. So we can write it as amplitude is still 5, the period is still 12, but we moved this one to the right 3 plus 16. The second one is about an oscillating spring, up and down, up and down. An object suspended from a spring is oscillating up and down. The distance from the high point to the low point is 30 centimeters, and the object takes 4 seconds to complete 5 cycles. For the first few cycles, the distance from the mean position, d of t centimeters, with respect to the time t seconds, is modeled by a sine function. After the first few cycles, then perhaps it would slow down and not be the same equation as it is at the beginning. So let's graph that model first before we try and determine the equation. So what do we know before we attempt this graph? We know the distance from high to low is 30. So the amplitude, which is always half of that, is 15. So the axis of rest is at 15. We also know about the time. It takes 4 seconds for 5 cycles. So the period, which is the time for one cycle, is 0.8 seconds. Let's put what we can onto this graph. We have our height in terms of time. We would like to indicate seconds with space to spare. We know that in this time, in 4 seconds, we should be able to draw 5 cycles. So every cycle will take 4/5 of a second. We also know that the difference in height goes from 0 to 30, or at least that's how we've laid our numbers out. The lowest, the highest, and the axis in the middle. I just like to draw a dotted line so I can center things a little bit. Dotted line in loose quotes. All right, here we go. It said it could be modeled by a sine function. So I'm going to draw it just like the parent sine wave. So I'm going to draw it like a sine function, which starts as we head upwards. So I'm going to start at 15, and I want to do a cycle in 4/5 of a second. So here it goes. We are headed upward, back to the middle, downward, back to the middle. Okay, here is one cycle. Best I can. We would draw another 4 of those within that space of 4 seconds. I personally find the graph helpful when creating the equation. So our equation, h of t, I know I'm going to write it as a sine function because I was told it could be modeled as such. I need the amplitude. I need a number that's going to allow me to find the period. I want any phase shifts would come in next. There aren't any. And I need any vertical shifts or displacement would come at the very end of the equation. All right, this is not an upside down sine function, and it has an amplitude of 15. So that's the easy part. The displacement's not bad either. The whole thing would be up 15. And lastly, I need a number right here that if I divide 360 by that number, I get 0.8. If I were to multiply both sides by b and divide both sides by 0.8, I would just be flipping these two, and b is whatever 360 divided by 0.8 is, which is 450. So to get a period of 0.8, I need the number 450, and that is my equation. Last question, of course, has to be a Ferris wheel problem. The Carnival Ferris wheel with a radius of 7 meters makes one complete revolution every 16 seconds. The bottom of the wheel is 1.5 meters above the ground. Find a function of the person's height relative to the ground, starting when the person gets onto the Ferris wheel. So what do we know? We know that the lowest, and I guess this is so people's feet don't get chopped off, is 1.5 meters above the ground. And we know that the Ferris wheel has a radius of 7 meters. So if you have Buddy on the bottom, here we've got a Ferris wheel. You have a Buddy on the bottom, they're 1.5 meters up. Then when they've traveled all the way to the top, and the radius is 7, they are now another 14 meters in the air. So your maximum is 15.5 meters. If I know the range of values, I could find the axis. It lies in the middle between 1.5 and 15.5. So we can average those two numbers to get the axis. 1.5 and 15.5 is 17. 17 over 2 is 8.5. My axis is 8.5. So when Buddy is right here, he is 8.5 meters in the air. What else do we know? We know that the period is 16 seconds. Because it goes through one revolution every 16 seconds, which sounds absolutely dizzying to me. The period is 16 seconds. So we're going to have to adjust our equation to get a 16-second period. I think that is all that we know. So let's draw it quick and come up with the equation. We have our lowest value as 1.5, our highest value as 15.5, with 8.5 running down the middle. We're to start our graph when the person gets on the Ferris wheel, so that would be at the lowest point. It takes 16 seconds to complete a revolution, so it would be one cycle from 0 to 16. So our graph would look like and so on. This can get me started to write my equation. The height of the person in terms of the time. First of all, I have to decide whether I want to use sine or cos to model my function. I like the look of this one for cos because it starts on a minimum value, and my parent function for cos, starts at the maximum, so this one would just be upside down. Upside down cos, negative. The number that I need in front of cos indicates my amplitude, and that would be 7. So I've got my minus 7 cos. I'm going to leave the hard one for a minute. I need a number in there that's going to help me with the period. I'm going to end my function with the axis. We have moved this parent function up 8.5, and now we have the hard part. What number do I need there that will change my period from 360 to 16? 360 divided by that number gives me 16. Working in reverse, I can get that number by 360 divided by 16. That number is 22.5. And lastly, just if you don't like to use cos and you wanted to use sine for this one, you can certainly use sine. The only thing that would be different, whoops, I won't put a negative there. Okay, the other only thing, the amplitude would be the same, the displacement would be the same, but you would have a phase shift. The 22.5 would also be the same. But you would have a phase shift because a sine function starts right where that blue dot is. And so this one, which starts at a minimum, would have a phase shift, if you were to write it as sine, 1/4 of the journey, which would be 4. That would be t, and I want it to the right, or if you wanted to write it as a sine function. On page 391, number 4, 6, 10, and 11.